Hello YouTube, and welcome to this demonstration of how digital filters work. I think by the end of this video you will have a solid idea of what digital filters are made of, regardless of if you have studied any DSP or not. And the reason I'm confident you can follow along with this tutorial without any prior DSP knowledge is because I built this filter with the most basic components in Ableton. This is really just using these different tracks with volume control and this delay, using the sample delay. Let's first walk through a block diagram of what we want to build in Ableton. So we're going to start with a sawtooth waveform, or really any input, and then we are going to have 3 duplicate copies of this sawtooth. The first channel will have no delay, it's our dry channel. The second channel will have 1 sample of delay, and the third channel will have 2 samples of delay. And when I mean 1 sample of delay, with a sample rate of 48 kilohertz, that will be 0.02 milliseconds of delay, which is the smallest resolution you can have. Then for each of these channels, we're going to adjust the volume very precisely and sum them together into our filter output. Finally, to create an IIR filter, we are going to feed the filter output back into another series of delays, adjust their volume precisely, and send that back into the filter output, creating a feedback loop. I think that's so cool that we can create digital filters with just precise control of delay and volume. But one technicality I want to mention is that when I mean adjusting volume, I also sometimes mean inverting the phase of the signal, so turning that upwards facing saw into a downwards facing saw. And that is because there's some negative numbers that we'll run into as we get deeper into this video. So by the end of the video, you should know how to build this filter in Ableton from scratch. But before we dive into the details, let's just walk through this filter I already built so you can get an idea of how simple this really is. So our input to the filter is going to be this serum patch with some MIDI chords. And we can listen to what that sounds like by soloing this bypass track. So that's what it sounds like raw. Obviously a saw wave, very bright. But if we unsolo everything, the bypass is now disabled, and it will instead, serum will instead get sent to this filter input, and it will sound like this. So obviously much less bright now. We've implemented a low pass filter. But there's no like Ableton stock low pass filters or third-party low pass filters on here. It's literally just tracks with volume automation and sample delay. So let's dive into why you can create a filter with just those 2 things. Okay, so in the intro, we saw that with just 5 tracks, we can implement a low pass filter as long as we have precise control over the volume and the delay. And by the way, this sample delay that I'm using over here, it's really just the same thing as a regular delay. It's just more precise. You can see that this regular delay plugin, at least in Ableton, it only gets down to 1 millisecond. Whereas this sample delay in Ableton, or the track delay, you can see 1 sample is equal to 0.02 milliseconds. So it's much more precise than this delay. There are some third-party delay plugins which can get down to sample rate. Like it's not like you only need to use Ableton's. So if you're following along with a different DAW, you could use this Voxengo sound delay, or really anything that has precise control over delay. Okay, so with that out of the way, let's look at a simple example where we're just using 2 tracks instead of, at the end of this video, we're going to use 5. So when we only have 2 tracks, what we get is a comb filter. And it's called a comb filter because if we play this, look in the top right at this spectrogram, you'll see there's kind of a comb shape that comes out, where the comb is, you know, like the hair comb that you put through your hair. You get these little notches. Let's take a look at an example to see why short delays give comb filters. So I'm going to resample this sine wave, which is playing a G1. And if we zoom in on it, we can see that we want to see the distance between the biggest part of the wave, the maximum, and the minimum part of the wave. And we can see it's more or less 3 milliseconds. And the reason we want to know that time is delaying this specific signal by about 3 milliseconds and then mixing it with the original signal will give you phase cancellation. So if we set this delay to 3 milliseconds, we now play this waveform again. You can see it's actually around 2.6 milliseconds. That we get the phase cancellation. But that's specific for this note. So if we were to instead play, let's say, go up a few notes to a C, this 2.6 milliseconds delay does not give you a phase cancellation for the C. So if you were to map this all out, I mean, that's exactly what this white noise is doing for us, because white noise is it contains all frequencies. So that's exactly what you're seeing, is you're seeing all the spaces that get perfectly phase canceled by this 2.6 millisecond delay. So basically what we're going to do for the rest of this tutorial is figure out how we can take this comb filter idea and build up on it to create a low-pass filter. All right, now that you've seen how the comb filter works, we can extend that concept one step further to create a very basic low-pass filter. This low-pass filter won't have the highest performance, but it's literally just the past comb filter example that I showed you repeated 32 times. This process is also known as convolution, where we delay samples, adjust their volume, and then add them together to cancel out certain frequencies. And I've repeated that up to 32 delayed samples, all with their volumes very precisely adjusted. First, here's what the white noise sounds like again. And remember to look in the right-hand side of the screen to look at the spectrogram and see all the frequencies present. And then when we apply the filter, we've really just cut the high frequencies. We haven't completely filtered them out. Around the cutoff frequency, you can see it starts to slope down like a low-pass filter, but then it kind of comes back up. And the reason for that is what this low-pass filter is really just a bunch of comb filters. And all the kind of notches of the combs are spaced out in a way that they try and cancel out all of the upper frequencies. But for this type of filter where we don't have feedback, this is called an FIR filter. And this particular one also has linear phase. If you've heard of linear phase from like Pro Q's EQ or other linear phase EQs. This type of filter requires a lot of tracks if you want to get good cancellation. I think in this not so well performing filter, it's almost easier to see how this is a bunch of comb filters because you can see in these upper frequencies, especially as we mess with these parameters, you can see how really this is just a bunch of comb filters in the upper frequencies. And for only 32 parameters where the volume was before, that was kind of optimal and getting like the least amount of distortion in the upper frequencies. But if you were to, where you'd go from here is you either add more parameters if you actually had like a, DSP program where you wasn't such a hassle to like manually add tracks, or you'll do what we're going to do in the next section, which is create a biquad filter where we use filter feedback and only need 5 tracks. But before we get to the biquad filter, I want to talk about something that we've sort of skipped over. So something I keep mentioning is how these filters can be implemented by precisely adjusting the delay and volume of different copies of the input. But something I have glossed over so far is how would you figure out how much to adjust the volume? And there's a reason I glossed over it, and that's because it's by far the most complicated part of the filter design. But I also think it's okay to gloss over it for the most part, so I'll just really quickly touch on this part of the video. Diving completely into how you get these, what they're called filter coefficients, is really quite complicated, and I think it maybe even requires like graduate school education to like fully grasp. But also, I think it's okay to gloss over it for the purposes of this video, because after all, what I said was this video is for kind of like producers, mixing engineers that just want like a simple way of seeing how filters can be implemented with tools that they're familiar with. Like you can just filter it with, volume and delay in your DAW. But like getting these coefficients, I don't think you really need to understand how that works to see that how the filter does its job. Because it's still true, the filter is just a bunch of comb filters. But for the purposes of this video, I think you can just trust that we can get these parameters of a filter by just following some formula. So in this case, I have a Python script where you just tell it the cutoff frequency, the order of the filter, which means the number of copies of the signal, or the number of filter coefficients, and you tell it the sampling rate, and it returns what we commonly refer to as the B coefficients, which is just the amount of volume adjustments. Normally, these B coefficients would be something you just multiply with the signal. Volume adjustments are a little different. In Ableton, we use like decibels. So I also just have a simple conversion to convert these B values into decibels, and for negative values, I print out whether these values are negative, which would mean we need to invert them. So if I run this script for a 250 hertz filter with 33 coefficients, it'll crank out all the parameters. These would essentially be how many decibels you put in your DAW for each track, and this is for how many samples of delay goes with that volume adjustment. For this linear phase low pass, none of them are going to be inverted because none of them are negative numbers. And this also plots out the expected filter response. And you can see here, even in this Python implementation, we also have that comb filtering in the what's called the stop band. Like essentially, after the low pass filter works, you can start to see where the comb filter is. So that is all I will touch on for how we generate these parameters. So the last filter I'm going to touch on is the biquad filter. And this is the same filter I showed at the beginning of the video. And it is a type of IIR filter, which you might have heard of. It stands for Infinite Impulse Response. And you might be wondering why it's called Infinite Impulse Response when it only has these 5 parameters or these 5 tracks in Ableton. And the reason for that is because this is where we're going to introduce the concept of feedback. And the reason feedback is related to an infinite impulse response is, well, let's just take a look at the signal flow. This IIR filter has the same signal flow as what I described in the beginning of this video, but let's quickly recap. The sawtooth gets sent to 3 parallel channels. The first channel is dry with no delay. The second channel has 1 sample of delay, and the third channel has 2 samples of delay. The volume of each of these channels is precisely adjusted and sent to a filter output, which I'm implementing with an Ableton send track. The filter output is fed back into 2 other tracks, which have 1 sample and 2 samples of delay respectively. Their volume is adjusted and sent back to the Ableton send track. Note that Ableton automatically has 1 sample of delay whenever you try and add feedback, so that 1 sample of delay is already built into our feedback path. So as I mentioned before, if you want to turn this biquad filter, or really any filter design, into something that you can control, you need to know how to get these filter coefficients out. So I have this script here which generates those filter coefficients. But if you really just want to know how filters work, just know that like inside of any EQ or any filter, there's just some formula that gives you the coefficients, and they tell the filter how to adjust or like how to adjust the volume or which values to multiply each delayed sample by. So I can run this, and I have the setup for a cutoff frequency of 500 hertz, filter order of 2, which actually means 5 coefficients, and a Q factor of 0.7. And this is the type of response we should expect to get out of this filter. And for the most part, you can just trust this. You don't have to dive into the math, but one thing I wanted to mention while we're kind of playing around with this Ableton implementation is that the cutoff frequency only appears in this D parameter, and that D parameter is only in the second coefficient for each of these. So it's in this B1 and A1 coefficient. So if we adjust the volume accordingly, we can control the cutoff frequency. So here's our X1 channel and our Y1 channel, and you can see the volume is set to the same amount. Well, actually, first let's just mess with the gain. So yeah, we're adjusting the cutoff frequency by just changing the volume of this X1 channel and this Y1 channel together in unison. Another thing you might notice is that the volume is changing. As I open up the filter, it's actually getting quieter. And that's because these filter coefficients, you actually need to normalize them if you want them to stay the same volume, and that would require changing all of these parameters, all of these volume adjustments at the same time, but like in different directions. So it would be hard to show in this Ableton example. So you just have to deal with the fact that this filter gets louder and quieter. And then I can show you, just since we know that adjusting this volume slider for X1 and Y1 changes the cutoff, I have mapped this LFO to the gain on this X1 channel. You can see it's right here, adjusting. And on the Y1 channel, it's adjusting the gain the same amount. Listen to what that sounds like one more time with the LFO running. Pretty cool. It's super simple. All you need is volume and delay, and you got yourself a filter. All right, it is time for some bonus fun at the end of the video. First off, thanks for making it this far in the video. I know it's a little bit of a dry topic for a lot of people. Maybe not everyone's cup of tea, but for me personally, I've always really liked both math and music. And I did study DSP in college, and I remember that like kind of something clicked as this was all happening, as I was learning all of this stuff. And it was probably some of like the happiest moments of my life, just because I don't know if you can relate, but just like when there's a couple, maybe like 2 or 3 things that you're really passionate about and they all start to fit together and make sense. It just kind of reminds me of like that, like Oppenheimer, if you've seen the Oppenheimer movie, like, can you hear the music? Like, do you see all the underpinnings of how things are working? I remember like when things started to click of how you can adjust frequencies and kind of manipulate sound, like that was kind of such a joyful moment for me. Which if you don't like math, I totally get that for some people that sounds like torture. But for me, it was honestly like joyful. So that's one of the reasons I started this YouTube channel, is I kind of like wanted to share that joy with other people that might similarly like learning like what are the underpinnings, like how does this music technology work? And honestly, I kind of get to re-experience that joy by making these videos because honestly, I feel like I'm understanding this stuff all over, like it's or relearning all this stuff all over again. Because when you haven't been working with it for a while, you can take it for granted. And when you try and learn it well enough to explain it, you sort of have to relearn everything. So I've had a lot of fun making this. Anyway, aside from that, this is the bonus fun at the end. This little block diagram here is something I'm very brand new with, so that's probably why it looks so ugly, but it's called Max for Live, and apparently you can program a little bit of DSP in it. So it should be, I mean, if you have the full Ableton suite, you can make this yourself. You just like load this like max audio effect. That's all I did, is I just loaded this here, and then you click this little box in the top left, and it opens up this window where you can start making your own audio effects. So this is kind of the culmination of everything we did in this video. It's the biquad filter, and they thankfully have the biquad implemented in Max for Live. Otherwise, we need to do all of that delay and multiply and feedback stuff, which actually that wouldn't even work. I tried that at my first attempt with a Max filter. Apparently, they don't even support feedback. If you try to feedback, or at least they don't support feedback with like one sample. You have to use like 1 millisecond or more. Otherwise, it just doesn't work. So luckily, they implemented this biquad filter, so you don't have to mess with any of the delay, the sample level control over delay. All you have to do is come up with those filter coefficients. And up here is, in the Python scripts, it's pretty much everything I showed over there. I ended up using a slightly different filter just because it was easier to normalize the gain of this type of filter. So yeah, like all this together, you have a frequency control up here. You can control the Q factor. If I now lock this and put it in presentation mode, there's just 2 parameters. We can even close this. Sure, we can save that. And I've mapped the frequency to an LFO. I don't know why Max crashed, but I'm pretty new to it. So maybe I just did something wrong. But yeah, let's play around with this. I've got this LFO hooked up to the frequency. I have the same little demo chord patch going, and let's see what the Max filter sounds like. Yeah, it's pretty cool. Neat that you can make this type of filter in Max. I still don't know if I probably wouldn't recommend doing that over just using a filter, unless there was like a specific type of filter, maybe that like wasn't implemented in Pro Q. Like there's really so many types of filters out there. So maybe like that would be the only reason I would consider using this. But it was fun. And another thing I'll mention is that you don't have to go to all this effort of generating the coefficients yourself. So that was kind of an exercise for like testing that all of this worked, and maybe something I'll use in the future. But I will show you pretty quickly that you don't need to use this, any of this. You don't need any of this. Let's get rid of all of this. Because in Max, they have this, I think it's called filter graph. And this buddy, you just take this and plug it into your biquad filter, and it generates the biquad coefficients for you. So if we go over here, I think we can choose a low pass filter. Yeah, so Max does give you like a visual way of generating those coefficients. And they've got like all these different filter types over here. It's pretty much anything you would need. And you should be able to control that with dials too. Like if you wanted to integrate that with something else. We can just try really quick if that would work. I haven't tested that. Oh, and interestingly, it looks like you can put the coefficients into here, which is pretty cool. Visualize what that would look like. Maybe we'll have to try that after this. So there's the cutoff. Oh, yep, it's working. And do they have a Q? Yep. So that's not sure that, oh yeah, that's working. So yeah, let's listen to what that sounds like. Cool. So I actually kind of like that. For the end of the video, it's kind of full circle. Like, it's just to say that like you don't really need to know how to do any of the fancy DSP math. There's always something to generate it for you, even if kind of you're making your own devices in Max. It's pretty easy to get something like that. What you really just need to know is understand how these work, because I don't think you need to go invent your own type of filter, but if you know that this biquad is really just, comb filters and feedback, it gives you a lot better perspective on like, why is phase introduced in a low pass filter? Well, it's just inherent to how a low pass filter works. There's just a bunch of phase shifted copies of the signal, and rather they're time shifted copies, and the time affects each frequency. The time shift affects the phase of each frequency differently. There's frequency dependent delays built into this. So that's just kind of how a digital filter works. We didn't talk about analog filters at all. There's also phase shift in those, but just having a grasp on digital filters, I think it makes you a better mixing engineer. Or at the very least, I think it's very interesting. I hope you enjoyed this video. If you did, please give it a like. It helps the channel out. Subscribe if you want to see more content like this. And I'd also be really interested to hear your thoughts on DSP. Leave me a comment if you want to talk more. See you next time.